CLion, a cross-platform IDE for C and C++. Download now.
Hi, I'm Anders, and I do love a good API. And I'm assuming you coming here, you also like good APIs, so I'm delighted to talk a little bit about what I think makes a good API, and for that matter, where there's maybe some opportunity for improvement. This is me. I work as a software architect at Tobii. Tobii is a company that does eye tracking, so we make sure that your car can warn you if you're falling asleep, or that your VR headset only renders the small patch of the screen that you're actually looking at and blurs out the rest, saving some CPUs. And they graciously paid for me to come here, so I'm very grateful for that. But let's do some API warm-up. Let's do some API design warm-up. So this is not going to be a deep technical talk. This is going to be focused on a little bit more fluffy substance. Do not let that confuse you. That is not the same as being easy. This is designing a good API is actually one of the hardest things that you will do, because it's about communicating. The good API design is about communicating with other humans, and more communicating with LLMs, like we saw this morning. But it is also about giving your users of the API a chance to express their intent clearly. So let's look at something easy to get us started. Mullet. This is, I would claim, an API. You can claim, okay, calloc, maybe realloc is part of this, but let's just look at these two together. It's a cohesive set of two small functions. Is there, let's just assume that we're coming up with this. Is there something we can do to improve on this from the beginning? Well, we start just briefly looking at it. We can see that there's an interesting asymmetry here. One starts with M, the other starts with nothing. So that's a bit curious. Let's put an M there. We're working iteratively now, so this is not its final form. Let's see what more we can do. So this type of symmetry here is an interesting aspect that we need to pay attention to. Actually, anecdote, there was an M-free function once upon a time in the 1973 version of Unix, where malloc was introduced. It was not used for memory allocation, not just, it was used for map allocations. So the M actually stands for map alloc. And map is something that you use to allocate both working memory and storage memory. And then there was an M-free function to free that. Somehow, somewhere, the M got lost, don't know why. Anyhow, let's just add it for symmetry. Second thing we notice is that we have for malloc, we have the size type, size t, where the name of the parameter is size. If you are just getting into programming, size, is that a byte size, or is that the machine word size? What is that? I mean, you probably already know that it's the byte size, so why not just say it's a byte size? I mean, the type already says it's a size, so okay, that's nice. There's also a nice property of size here. Has to do with fluidity of the APIs. So if types help your, or if your functions help your types flow into your API, that's a nice property. So size of produces a size t. That's convenient. In this case, maybe just a little bit of a stretch, because you might not just use size t. Also a little bit of a foot gun with the array sizes, but something to consider, at least. But M is very terse. Let's just say memory. Why not? Where the 120 is the new 80 line width. We can squeeze this in. But there's a trade-off here. No one says memory allocate unless you're like a computer. Memory allocate. You say allocate memory. And so that would read much better. Free memory, allocate memory. But in C world, we have a trade-off because we don't really have namespaces other than prefixing. So we use memory allocate memory free. It's okay. We all have to do trade-offs. Is this done? Well, of course, we can always do more, but this is warm-up. Just one final thing to mention is in C23, you have no discard. If someone doesn't allocate and doesn't use it, probably bug, right? So let's tell your users about that. There's something that is missing here, and that is what happens with the memory. Is it zero initialized? What happens if you run out of memory? How are errors handled? All of these things try to express in terms of the function names and so on, but here the second best thing is put a localized comment that explains this. This also helps the LLMs trying to figure out what you're doing by reducing the context window size, so keep it close to the functions, not just in some documentation somewhere else. All right, warm-up complete. Let's look at some principles. I mean, I sort of loosely touched on some principles when we were going through that, but let's be a little bit more systematic. What are some good principles for designing APIs? A lot of you are senior developers. You probably will sort of nod when you hear these, but I think it's good to remind yourself that these principles exist every now and then. Also, it's one thing to know these things, it's another thing to actually do it. So when I go through these, just think about the APIs you have in your code base and ask yourself, am I following this? And if not, then why not? First one, consistency. Consistency is good, right? We should have consistency in all sorts of different ways. We should have consistency of naming, for instance, of course, easy, first thing you think about. We should also have consistency in parameter ordering. Does your API take out parameters? Are they first or last? Be consistent. We should have consistency in domain. Is your API about databases or networking? It should probably be about one thing, right? There's like the I and solid, the interface segregation. It's a thing, right? We can afford to have more interfaces within reason, of course. We also have consistency in other ways. We have paradigms. Is your API blocking? Is it returning futures? Is it a callback-based API? Try to be consistent. Sometimes it's fine to have multi-paradigm, but make it like, so it's clear sections, or maybe even different APIs, so that you are consistent in this matter as well. A good API is also symmetric. Symmetric helps with predictability. If you have an open function, it's nice if you have a closed function. They are opposite words. If you have an open function and you have a destroy function, you are confusing this symmetrical linguistic thing. So try to find opposite words to do opposite things. You can also use symmetry. We will see an example of this. If you have something that is a clear opposite word and the other thing does not have a word at all, it's like a default. The human brain will sort of automatically infer that the other thing is the opposite. This is confusing. I will show you an example of this. So let's talk about a final thing here. Predictability. A good API is predictable. And the first thing that comes to mind is side effects. If I do something, it better do what I think it does. And what I think it does depends on a lot of different things. It depends on idiomatic use in the community at large. It depends on naming, of course. Again, naming, always naming. It depends on what the other things in your API are doing. So let's look at a little bit of an example. This is a stud vector. This is the stud vector empty method. I'm sure you've seen this before. Who in here are 100% sure that they know what the empty method does? Okay. It's not everyone, and that is unfortunate. Because there's also this stud vector clear function. Can we all agree that this is not an ideal, predictable, and well-expressed naming conception? So, I mean, it's unfair to harp on this because a lot of smart people have built this, but yeah, we've learned. We can do this, right? Is, has, can. It doesn't hurt. We can afford it. We can also do, oops. We can also do the no discard thing again on any getter. If you think you're clearing something but you're actually running empty, you could have a no discard, so it's clear that you're actually requesting something. Okay, anyway. I mentioned this briefly before. I think a good property of an API is fluidity. If you have a mix of functions and data types, which you typically have, make sure that the data types flow in and out of your functions and operations in a nice way. Don't force your user to perform casts. Don't force your user to have a lot of intermediate objects. Try to make sure that the ergonomics of it is good when it comes to type and parameter types. C++, right? Safe by default. Actually, a few years ago, I think it would be controversial to say that we should have things safe by default, even if it is a performance hit in a C++ heavy conference. I think no more. This has been a bitter pill to swallow for a lot of us, but I think now most of us are safe by default, camp safe by default, performant opt-in if there is a conflict. Let's look at a little bit more examples here. This is studvector again. Is this safe code? I mean, this particular line is safe, but we all know index operators is, you can shoot yourself in the foot. You could do unsafe memory access this way. We have this. Who uses this out of curiosity? Yeah, we have one. We have a few. Actually, much more than I thought. I have never seen this in the code base of any code I've seen. It does bounce checking, runtime bounce checking. So that's nice, but it's opt-in, right? And it also, there's another thing with this that bothers me, but it's not very symmetric. One is a regular function, the other is an operator. It's not consistent. And it's not very predictable. Where does it say that the @ actually does runtime type checking? How is it any different? I mean, it's just by looking at it, you can't tell. But let's take it a little bit at a time. First off, we switch it around, right? If we are to redesign this a little bit, the default now does bounce checking. I mean, I'm dreaming now. You can dream a little, right? So we switch it around. But then I'm still bothered by this asymmetry. And so how about this? Now we use the index operator in both cases. It's consistent. We have unchecked. Okay, it's clear what it's doing. It's unchecked, unsafe from Rust. You sort of get the point that you're in some kind of dangerous territory here. By symmetry, the other one will be read as checked. Because if you have something unchecked and you have something else, the other thing is supposed to be checked. That's how your mind works. If it isn't, then you need to address that fact as well. So this could be a good design. I mean, not for studvector. Vector is the way it is, but just as an aid thinking about these things. Complete is another interesting thing. I mean, I'm all for keeping interfaces small. They should be small. They should be like sweet, succinct, to the point. But there is also something to be said for being complete. We have the rule of 5. We know about this. But there are other things. We have the index operator. We just saw the index operator. When you implement the index operator, it usually makes sense to implement 2, right? You have the const version and the non-const version. Make sure you sort of have a rounded, complete offering to your API users. All right. These are some prisms that you can use to view your API through. Please do that and see what you come up with. How are you scoring on all of these? Take them to your API and check them out. The second part of this is that there are like design patterns, of course, for API design. we all know like the facade pattern. We know other types of patterns. Some of them more geared towards implementation, and some of them geared more towards API design. So I'm going to be covering one, maybe two if there is time, but let's start with one. The mullet. This is this is me, yours truly, sporting a beautiful haircut, maybe peak haircut. The mullet was that. Yeah. The mullet is business in the front, right? Part in the back. This is a great design pattern for APIs, as it turns out. You have your series API, but then you have your party API behind it. And then you have your implementation. Okay, so ABI compatibility is hard when you distribute binary libraries, right? So C is sort of the king of ABI compatibility, no matter what we like to think as C++ developers. But all is not lost. We can have a serious C ABI that we give to our customers. And behind it, we can have a much nicer C++ API that we actually use for our implementation. So the customers see this, ABI stable, never changes, very nice. This is actually also an interesting realization I recently had, that downstreams, your customers are technically downstream consumers of your API. But there is a stream actually in this context that runs both ways, because you are financially downstreams from your customers. And sometimes you can decide what to change, but usually they decide if you can change the API. So the power dynamics here is not one way. So if you are in this situation, this is what you can do. Your internal C++ party API, you can use for all sorts of things. You can use it for pocking your internal stuff. You can use it for testing. If it's just a thin facade, then why not? You can use it to create bindings for other languages, your Python bindings, your Lua bindings, whatever. You can use it for internal experimentation. You can build internal tooling on this. But what's more, you can also use it for version evolution. So if you want to release a new version of your Series API, but your customers won't upgrade, well, you can have two Series APIs. That's okay. Just create another one, put it on the top. If it needs to change, if you need to evolve, just make a small adapter. It's usually fine. This is super useful, especially if you have a shared code base and you have multiple customers that want different types of APIs. This is a great pattern to use, the mullet. How is it different from just a regular facade? Well, actually, it's not, but the intention of why to use it is, I guess, the selling point of it. We actually do have a little bit of time, so I'm going to skip past. This was all I thought we would have time for, so thank you. But let's move on to some bonus numbers, actually. The domain burger. This is another pattern. That is, if you're into domain-driven design and read Evans Blue Book, etc., this will be a little bit familiar to you. But bear with me. You have two breads and a patty, and in your project, you can divide your APIs into tech, core, and project. And this is a useful way to think about APIs in your, usually you have more than one, right? You have, for a big product, the product consists of many, many APIs. And the tech APIs, they are sort of grouped in different, and the ideal is that they do not intersect in their API language space or whatever. They just intersect in their implementations. So the tech, the base of this is sort of a layered architecture for API naming, I guess. Here you have a vernacular like databases, file systems, networks, whatever. Your core API or your core domain, this is where you have things in Tobii. We work with eye tracking. So this is where we have eyes, we have corneas, we have gaze angles. This is the world of our domain. This is not the world of data. We don't have eye database in this domain. We have eyes in this domain. Of course, they might be stored in a database, so the implementation might use a tech, but the APIs should be about the domain. We have the project domain. We did eye tracking integrated into Sony VR2 PlayStation headset. So then, of course, we had a small API for Sony to use. And that is an API that's very small and specific to a specific customer. But it's not really our domain. That's more of a delivery of the domain. And you have dependencies going down. Again, this whole idea of layered architecture is old, but this is not really the same thing. This is about layered domains in your APIs and trying to keep your APIs to one domain and trying to keep your domains in this type of relationships. Yeah. So this is the domain burger. Can be something to ponder. And since I was so fast, I will move back in time and thank you all for letting me talk about APIs and API design. Thank you.